You know, it's hard to kind of condense all of kind of at different various aspects, not every aspect, but various aspects of astronomy into just kind of like a 3-week sort of session, but that's what we're doing. We're talking about the solar system. We talked about how the solar system was formed. And we talked, actually, this is a slide talking about the dude named Kepler, Johann Kepler, and he was the guy that actually came up with 3 laws of how the planets orbit the sun. So this is the sun, right? Here's the sun, and how do the planets orbit the sun? Now, we're going to be talking more about the individual planets coming up, just kind of briefly hitting them. But what Kepler's last law basically said that, well, you have it says the more distant the planets orbit from the sun, okay, more distant planets orbit the sun at lower, slower average speeds. So basically, you guys told me the other day that we get Jupiter, Saturn, Uranus, Neptune, kind of the gas giants out here. The farther they are, the slower they orbit. And I guess I would draw your attention to this first column right here where it says P, period. Okay, so for instance, Earth takes one year, okay, 1.00 years. Mars takes about 2 years to go around the sun once. Jupiter takes about 12 years. Saturn takes about 30 years to go around the sun once. Uranus 84, Neptune 164 years to orbit the sun once, and Pluto about 250 years to orbit the sun once. I just thought that was interesting. Okay, so I only have 2 slides on the subject of, and I'll unzoom it here if I can find the unzoom thingy. I only have two slides on the sun. And actually your textbook covers the sun in a different chapter, probably the next chapter. We're going to be talking about stars, and I think your author, the textbook actually brings the sun to talk about when it talks about stars, but I want to talk about the sun and the solar system. So when our solar system formed, basically the thing at the center became our sun. The thing at the center, okay, when our whole solar system was forming, actually got like 99% of the stuff ended up being, because of gravity, pulled it right there. So when we talk about other stars in the next part, we can kind of compare them to our sun. But what stars are doing, including our sun, is basically that if this is the sun, only in the core of the sun, and actually I have a kind of a picture here to kind of show you what what our sun looks like inside. Only in the core of the sun is it hot enough and is it packed close enough for basically nuclear fusion to happen. Okay, and I can't remember, I bet I have it on the next slide, maybe I don't. So let me just go ahead and tell you what nuclear fusion is in a nutshell. Okay, we talked about elements, and actually this is kind of where chemistry kind of is helpful. We talked about elements, and the simplest element is H for hydrogen. What the sun is doing here in the core is basically taking a hydrogen plus a hydrogen. You know, we can write it kind of as a chemical reaction to form a helium. It's a little more complicated than that, but basically it kind of makes sense. If you look at the hydrogen, it's got 1 proton. You look at the helium, it's got 2 protons. Okay, so again, it's a little more complicated than that, but just overall we can kind of think of that. And the cool thing about it is it's amazing. If you were to weigh these 2 hydrogen, I'll call that M1. The mass of those 2 hydrogens are M1. And if you were to weigh that helium, I'll call that M2. And we can, and they do. What they do is they find out they lost some mass. Okay, so this is to say that M1 is bigger than M2. What does that mean? Basically, it lost some mass. It lost some mass. And it's not like an accident. It's not like, oh, they didn't do the experiment right, you know. Our sun is losing a lot of mass, and it is converting it into energy according to Einstein's E is equal to mc squared. Sounds like a rap group, but. Okay, so E is energy, and this would be nuclear reactions. Create energy from this missing mass, and M here is mass. I think we ran into C before. Do you guys remember we talked about all those cousins, those different forms of electromagnetic radiation? C, we said, is the speed of light. Which is a pretty big number. Okay, so that's what's happening in the core of our star. the sun, and that's what happens happening in the core of all stars. So basically, it's hottest there, and then it gets cooler. There is one exception. It's hottest in the core, and then it gets cooler as you go out to the surface of the sun. So a little bit about the zones of the sun, or the interior zones. We have the core, and then we have the radiative zone, and then we have the convection zone. And basically, I'm going to do a purple here. From the core, that's where our energy is created. Energy moves outwards. So this little squiggle here is energy. I'll put E for energy, is moving outwards. And it moves through the radiative zone, kind of butt to butt to butt. It moves through the convection zone by chunks of moving stuff. Okay, so once you get out to the convective zone, okay, after the convective zone, then we kind of have more of features of kind of the surface or the atmosphere of the sun. So numbered or listed here in order that they appear, the photosphere is basically kind of the skin. That's the sun's skin. That's what I think of the photosphere. And then the sun is kind of a strange sort of thing. You really can't stand on the sun. It's definitely not a solid, and it's not really a gas, and it's not really a liquid. A lot of the sun is what we call this plasma stuff. Okay, so the chromosphere and the corona are definitely gases. Sometimes I spell gases with 2 S's, sometimes with 3 S's, but so here's another diagram of the sun. The red thing in the center is the core. That's where the energy is being created. And then you can kind of see the yellow next to the core, and you can kind of see the orange next to the core. The yellow would be the radiative zone, and the orange would be the convective zone. And so you see the red coming out, that would be the energy coming out. Now, the green going in actually is gravity. Gravity doesn't always have to be green, okay? But one of the things, in order for, when our solar system formed out of the solar nebula some 4.6 billion years ago, gravity was an important thing to basically make things come together. Whether it was the humongous sun or was the individual planets, gravity made them kind of come together. So we have those two forces going on in the sun. Thursday, I'm kind of on the fence a little bit. What I'm hoping is that Thursday will continue to be clear. The forecast now is for clear, and I will get the telescopes out and we'll look at the sun carefully. And I'll tell you Wednesday for sure, closer to time, but probably a good place to meet. I haven't decided whether I usually meet like out there on the other side of the parking lot because there's a nice place to spread out. No one's out there. Alternatively, if it's easier for me, I might drag my telescopes up the hill. But even if I said drag, I know I'm kind of thinking over there because I can take my car and go up there. So I'll let you know. But there's a good chance the Thursday lab will be out there on the hill. Okay? Kind of. I'll set up a couple of telescopes and we'll look at sunspots. So our sun in the photosphere, remember I said that was the skin of the sun, basically? In the photosphere, sometimes they have these blemishes. Not always, okay? So what you're probably drawn to is that big black thing, if you're like me, okay? That would be the blemish. This thing right here is the sunspot. Now, after you're done looking at the sunspot, can you look around and see these kind of little things right here? These little things, if I could have a video of this photosphere, the surface of the sun, actually you would see those kind of, they're called granules. You would see those granules kind of ebb and flow. Each little granule like that is about the size of Texas. So that kind of gives you an idea. Sunspots in general, this is a close-up of a sunspot on the sun, are about the size of Earth. Okay, so granules are always there. So the black thing's a sunspot. These red things are granules. Okay, and they are always present. Sunspots are transient. Transient means just they kind of come and go. Okay, and we're hoping on Thursday we'll see some sunspots. So can you see this disk of the sun over here? Okay, and see sunspots? Actually, this is I hope we'd be this lucky. Usually, this is the disk of the sun. Usually, the disk of the sun doesn't have this many sunspots. But those are some honking sunspots. Often, or sometimes they come in sunspot groups. Can you see kind of a group of sunspots? So sunspots are transient. They're not always there. And actually they have a pattern. I'm going to show you that pattern here in a minute. But if you see sunspots, that means that you have an active sun. Oops. There we go. If you see sunspots, that means you have an active sun. I mentioned that because if you see any of these other things, you also have an active sun, and they are also transient. So, for instance, we have, let's see, solar flares. Solar flares are basically, you have a pair of sunspots, and basically you kind of have a loop-to-loop of plasma coming from the sun, and that's kind of the activity for a solar flare. Prominences, filaments, coronal mass ejections are the biggest granddaddy of them all. If you're into destroying the earth, that sort of thing, if you're into, oh my gosh, our whole power grid's going to go down, that sort of thing from the sun, that would be a coronal mass ejection coming from the sun. And what it is, and I don't know if this is necessarily one, but does it look like that is like a chunk of material from the sun that is just maybe itching to be sent on its way? No. If I could animate it, it might. If something gets far enough away from the sun, it basically, gravity doesn't have a hold of it anymore. The sun doesn't have a hold of it anymore. So, especially if it's got a little bit of, we talked about momentum, if it's got a little bit of speed, okay, it can actually leave the gravitational influence of the sun and come shooting at the earth. All right, so like this slide says, there are all sorts of spacecraft studying the sun. So, with regard to the transients of sunspots, so sunspots aren't always there. Coronal mass ejections, filaments, solar flares aren't always there. They actually have an 11-year cycle. So that last little figure I put up, actually along the y-axis, these are actually dates or years. Okay, here we have the year 2000, looks like 2005, 2010, 2015. 2020. Along the y-axis is number of sunspots, or just somehow looking at solar activity. So basically, the sun's activity ramps up, and then it comes down, and then it ramps up, and then it comes down. If you've ever been to an IMAX theater and seen the video Solar Max, okay, basically what they're doing is they're talking about when is the sun most active. Okay, so when the sun's active, you see lots of sunspots and lots of these other things. This website, spaceweather.com, is a good one. Let's see if our internet works today. Spaceweather.com. And that's where I'm going to go on Thursday to see if we're going to see anything with regard to sunspots on the disk of the sun. So Thursday's lab, I have basically the telescopes have something you put on the end of them. I have a third telescope that actually is for looking at alpha hydrogen lines from the sun. So So this is the website I was telling you about. So this is like real data. It's updated, daily. So you can see down here in the corner that this is a disk. This is what the disk of the sun looks like right now. Okay, and so if we were to have the telescope set up right now, we would see those little sunspots. Down here, this is a great website. They have an assortment of things. Right here, it looks like they are highlighting it's called a conjunction, when things get together. They're highlighting the planet conjunction this morning, or right now in the morning sky. You see Venus, Jupiter, and Mars. And actually, little shy Mercury is kind of underneath there, too. Very pretty. This is also a really good place to go if you want to know about your northern lights. Like northern lights, of course, you kind of look north. Northern lights are directly associated with the sun's activity. If the sun is kind of extra rambunctious, extra sunspots, it can be sending us charged particles. And actually those charged particles cascading through the Earth's atmosphere, that's what gives us our northern lights. So down here at the bottom, if I scroll on down, it will show us that. Okay, so right here, the kind of green swatch right there is the folks that are going to be privy to northern lights. And of course, down here in southeast Iowa, we aren't getting it right now. But just let the sun ramp up and we'd be more likely to get them. This caught my eye too. I'd never seen one of these. It's a photograph of kind of the up part of a lightning bolt. Is that not cool or what? All right, back to the show. Maybe. Okay, so that's all I got about the sun. So then I have a couple questions about the sun. Like I said, it is in like the next chapter, but it's page 543, short answer. Questions number 7 and 11. That was a quickie about the sun. Now, back to the planets. I have one slide per planet coming up. But before I do one slide per planet, let's look at all the planets together. Aren't they adorable? Not drawn to scale. This photo is not drawn to scale. One of the things you may have already learned in another science class or just from being out there is that the order of the planets, okay? The other thing is that we have 4 planets that are very similar, and they are called terrestrial planets or rocky planets. Terrestrial planets would be more, but they are rocky. You can stand on them. Mercury, Venus, Earth, and Mars. And then after that, with regard to planets anyway, we have 4 planets that are similar also. So it is kind of nice Pluto's not there because, you know, the odd man out, right? We have 4 and 4. So we have Jupiter, Saturn, Uranus, and Neptune. And they are kind of paired, I think I said the other day. It seems like Jupiter and Saturn kind of have that orangish hue to them, orangish red. And Uranus and Neptune are kind of bluish. But all of the gas giants, or the Jovian planets, they all have rings, okay? And belts and zones. And actually, this slide emphasizes, I think it's kind of funny, these gas giants all have a little terrestrial planet in their belly. They do. They have a rocky core, icy rocky core. So let's see if I can make this a little bit bigger. I'm playing around with this. Let's see. So here's a little bit of statistics about the first 4 planets anyway. Okay. The first column is how close they are to the sun. So one of the things I want you to know in this class is how do we judge distances in space? Well, one way we judge distances in our solar system is an astronomical unit, an AU. Not to be confused with an atomic unit. Astronomical unit. So an astronomical unit is basically the average distance between us and the sun. So it makes sense that Mercury 0.4, Venus 0.7, Earth 1 AU, Mars 1.5. Now Ceres, I guess we haven't talked about Ceres yet. Ceres actually, maybe we did. Ceres is actually it's a dwarf planet. On my slide right. Ceres, it's a dwarf planet, just like Pluto, but Ceres, and you guys told me the other day, I think, that between Mars and Jupiter is the asteroid belt. So dwarf planet in asteroid belt. I have a picture of Ceres coming up. Let's see, what else? Oh, here's one. I don't know if you think this is interesting too. Oh, not that one. This one. Okay, rotational period. That's how they're spinning. Okay, rotational period. How long does it take them to spin on their axis one time? Okay. With regard to, oh no, that's not right. Yeah, that's right. Okay, so in terms of days, not hours. So it takes Earth 1 day to complete one spin on its axis. Oh my gosh, check out Venus. Okay, so Venus is spinning on its axis of rotation. It takes 243 days for it to complete one rotation. You're like, Venus, could you go any slower? You know? Mercury's pretty slow, but not that slow. All right. Another thing, I like this, I do really like this, because look at the last column. Isn't that interesting? Sometimes you're like, well, okay, so what's the whole moon thing? What we got going on with regard to the other planets? Well, here's the tally. Mercury, no moon. Venus, no moon. Earth, 1 moon. Mars, and actually I'm going to show you a picture of Mars moons. They look like potatoes. I think I might have told you the other day. All right. So that's the first 4 planets and Ceres, which is actually an asteroid in the asteroid belt. So then we have the other 4 planets. Okay, so let's take a look at them. This is how close they are to the sun in astronomical units. Okay, so 5.2 astronomical units. So 5.2. So that it's like basically you take how far it is from the Earth to the sun times 5, and that'll get you to Jupiter. Neptune, you take the distance between the Earth and the sun times 30, and that'll get you to Neptune. Okay. Another thing we looked at was how long does it take to complete one rotation on its axis. And remember, like, Venus was, like, terrible. It's like 243 days. Well, here we go over here. How long does it take to complete one rotation on its axis? Definitely less than 1 Earth day. Jupiter is humongous. Jupiter spins on its axis once about every 10 hours. Completes one rotation on its axis. Dude, it's amazing. And then the last column up there, and I think we already kind of had a slide to indicate this, but over here, and the tallies will be different depending upon, with regard to moons, the tallies will be different depending upon the source you look at. But according to this source, 63 moons, really, around Jupiter, 60 moons, probably in counting, around Saturn, Uranus, 27 moons, Neptune, 13 moons. It actually, I do know that this is out of date. Pluto now has, I think, 5 moons, and there's a 3 there. Okay. Eris, actually, let's see. We'll get to Eris. Eris is out there by Pluto. All right. So let's unzoom so we can kind of see the whole thing. So before I get to 1 slide per planet, please, okay, I want to kind of just assure you that the planets have been, we're studying them. We're studying them, and also Europe is studying them. You know how we have NASA? That's our, that's our folks, scientists that are run by our government. Well, in Europe, they have the European Space Agency, or ESA. So we're not in competition by any means, I don't think. But these are actually the European Space Agency missions that have been out and about. These are, I don't know if these are necessarily the NASA. I'll see if I can zoom in a little bit to these. Try to kind of get a little, I think if you go over, put that in the middle, and then zoom. Something like that. Okay, so kind of orient yourself what we got going on here. Of course, hopefully you see the sun. And each one of those kind of little thing that looks like a gnat. Okay, here's the sun. Okay, and those little things that look like a gnat are spacecraft. Okay, let's see. We have, I guess they didn't draw in any orbits except for, they drew in the planet Jupiter. But remember I said that there are many spacecraft that are studying the sun? Here are some of those spacecraft. I guess it is Jupiter. Messenger is around Mercury. Venus Express, of course, around Venus. These stereo, A and B, around the sun. Maven, oh yeah, Maven is on its way, or is there, it's Mom, right? Mom and Maven, I guess, is our Mars missions. This mission over here, I know it's hard to read, D-A-W-N, Dawn. Remember I said that Sirius is a dwarf planet. Dawn is actually at Sirius right now. We have the Voyager spacecraft, Voyager 1 and Voyager 2. They were in the news within the last couple of years. They were sent up in the 1970s. They're leaving the solar system. Yeah, the SOHO, that's a great for the sun. I guess we have this is the Earth up here. So this is by no means all comprehensive. This is Mars over here. I don't know, I guess I see they're trying to show dotted line, kind of. This is to Mars right here. But anyway, Mars is a very busy place. The most recent Mars mission was Curiosity. Opportunity and Spirit were twins, and they're on the planet, so is Curiosity, but Spirit died. Opportunity's still going on. So, and then we have Jupiter, and Jupiter's a very busy place. So, all right, I don't know, it doesn't necessarily do it justice. And I had a website, I think you might have the same website available to you. If you're ever wanting to say, now, where are all those spacecraft and what are they doing? So starting with Mercury. Mercury is the planet that's closest to the sun. It looks kind of dead. And we do think that Mercury is dead. Dead planet just means that it's solid. You know, it means it has no volcanoes or nothing like that. It's very cratered. Mercury, to me, looks like the moon. In order to have an atmosphere, like Earth has an atmosphere that we appreciate, it needs to have a certain amount of mass, and Mercury's so little, it doesn't really have the mass to have an atmosphere. So the order of the planets goes Sun, Mercury, Venus, Earth, okay? So the deal about Mercury and Venus is that they are actually what we call morning stars. You're like, really? I thought they were planets. But something that is inner to our orbit, like Mercury and Venus is, we're only going to see them near the sun in the sky. So it's going to be as the sun is setting or as the sun is rising. Mercury, not much to look at through the telescope even. The biggest kick I get out of seeing Mercury is just to say, that's Mercury. And things that are like kind of close to the sun or low on the horizon, they always look red. I don't know if you've noticed before, if you've ever like looked at stars that are low on the horizon, they twinkle and they shimmer. Okay, for something that's kind of low on the horizon, that's just kind of the way it is because of the Earth's atmosphere. So Mercury usually looks pretty icky. It has a large feature called Caloris Basin, a big old impact feature. Now down there, the asterisks, one of the things I want you to know if you don't already kind of think about it, but Mercury, we can see Mercury, it's red and kind of ugly. We can see Venus really bright. Pick Venus. So the only way we can see Venus, it's not because it like has its own energy. Okay? The only way we see Venus is because the sun's light hits Venus and then that light comes back to us. Okay? So that's the only way we see any of the planets. Speaking of Venus, so Venus right now in the morning sky is very bright, totally bright. And what makes Venus in general very reflective is because it has, unlike Mercury that doesn't have an atmosphere, Venus has a thick atmosphere, and it's mostly carbon dioxide. And I'm not emphasizing it this semester, but I think your textbook goes in a little bit of detail that, you know, carbon dioxide is like, oh, it's bad on Earth. Well, carbon dioxide is warming the Earth, and that large amount of carbon dioxide in Venus's atmosphere is warming Venus. Okay. So not really, your telescopes, even if you have the most awesome telescope, an Earth telescope, even the Hubble Space Telescope cannot see through Venus's clouds. The best thing we can do is basically send something to orbit Venus like we have, and using radar kind of get a topography of the planet. That's the best thing. This little inset up there actually is a Russian, I think it was taken back in the 1970s. Okay, so we can, when we send spacecraft, we have some options. We can actually orbit or we can land, okay? And this actually was a Russian spacecraft, like I said, back in the 1970s when we were going to the moon, or they went to Venus. So as far as I know, that's the only spacecraft that's landed on Venus. And the conditions on the surface of Venus are terrible. They are like very harsh, very acidic, and terrible great pressures. Okay, so it didn't transmit for very long, but so Venus. We think that Venus is not solidified in its core. Okay, actually, I mentioned we kind of get a sense for the topography of Venus using like radar technology. So there are kind of dormant volcanoes. Venus is terrible with its rotation. It's like takes 243 days or something to complete one spin on its axis. Okay, so now one thing about Venus is it's different than the other planets, or most planets. If you look down on its north axis, actually it's spinning clockwise instead of counterclockwise. And we think actually this is related to the fact that it got hit early on and basically it did a 180, okay, on its axis. All right, on to Mars. So Mars is a very busy place. One of the things about Mars is it does, this is just one of many pictures that of the Martian soil, or the surface, and it's red because of iron oxides. So you're like, iron oxides, the word oxide, oxygen, oxide, you're like, well, okay, so where's the oxygen on Mars, right? Okay, well, it's not there anymore. Actually, Mars has a very thin atmosphere now. It used to have a thicker atmosphere, and that's what gets people so excited, you know, about what it used to be and what it is now. But so it's relatively thin atmosphere, has mostly carbon dioxide. There are a couple features on Mars, just like kind of there's like the Caloris Basin on Mercury. The couples of features on Mars I probably want you to know is this Valles Marineris. There's this kind of an inset of Valles Marineris. Actually, it's around the equator. You can't tell it here, but it's kind of around the equator of the planet. And this distance is basically from our west to our east coast. So this would stretch from California to our east coast. Okay? And it's like a trench. It's like the Grand Canyon. That crazy? That's in Mars. Another feature on Mars is kind of looks like a dormant volcano. Okay? Volcanoes, if you take a normal volcano and you take the top and you lop it off, you end up with kind of a flat sort of plateau thing. That's called a caldera, and that's actually what this is. It's about the size of Missouri. Okay, so it's a humongous, it's called Olympus Mons. So what else about Mars? People got excited. People call Mars like our sister planet, like Earth's sister planet, but actually Venus is more like our sister planet. But Mars is similar to how long it takes to complete one, like its day is similar. It's like 23 hours to complete one spin on its axis of rotation. And it actually, its axis of rotation is tilted, kind of similar to the Earth's. We talked about Earth's tilted axis of rotation. The other thing is actually, see if I have this. It does have these dust storms, and so you can actually kind of in the upper right-hand corner, if you look at this figure right here, that kind of gray-looking stuff is, it's a dust storm, okay? One of the things, though, if you've seen the movie The Martian, dust storms, windstorms on Mars, really, since its atmosphere is so thin, they aren't going to like blow over trees and things like that like they did on the movie. I guess that's one thing that's really scientifically bogus. An exciting thing about Mars is they have all those rovers on Mars. They are finding more and more evidence of liquid water. And this little thing up here That actually looks like an ice cap, and it actually is an ice cap, but it's CO2 solid. All right. Then the last thing about Mars is these are Mars, the Martian moons. Okay? They are the Martian moons. And they totally do not look like Earth's moons. And this type of moon is what we call a captured moon. Okay? A captured moon is kind of like, it sounds like, basically the planet was forming, and maybe after the planet was formed even, something rocky came close enough by to basically insert itself into orbit. Unlike Earth's moon, which basically kind of formed when Earth was forming. So those are kind of the two types of moons. So I've got friends at the observatory who like use the telescope and look at Mars, and I've never really seen much feature on Mars. I'm sorry. I'm not going to lie and say I saw it when I didn't see it, because I didn't see it. Okay. So, cool. Well, after Mars, we have the asteroid belt. And how many asteroids are there? Lots. Okay. But most of the asteroids are like thousands of miles apart. The asteroids in the asteroid belt, these are not the ones that we're tracking. These are not the ones that we're worried about are going to hit Earth. There's a different set of asteroids called Apollo asteroids. The asteroids in the asteroid belt are thought to be there because actually Jupiter's gravity was too big to make them kind of snowball into one object early on. So these asteroids kind of have their own little personality. Sometimes the asteroids actually have a little satellite or their own little moon. You've probably heard in the news that when it comes time to go into space, with regard to where the money's at, perhaps asteroids would be of interest. Landing on the asteroid and mining them and getting the material back, which is kind of an interesting thing to watch. The asteroids, even though it seems like there's a lot of stuff there, actually, if you were to combine it into one spot, it actually still would not be the size of a planet. So Sirius is, remember Sirius is a dwarf planet? This is Sirius. It doesn't really do it justice much. But this, it looks like a moon, but it is actually an object in the asteroid belt. It is called a dwarf planet. This is Sirius. And the spacecraft Dawn is orbiting Sirius. And there was a lot of excitement. There still is a little excitement, but you're like, that little white spot there. What is that? Okay, so on my list of things to do is to use the telescope and to find an asteroid, because you figure if planets can reflect light from the sun, so also can asteroids. All right, on to the gas giants. Jupiter, okay. One of the things about it is like a lot of stars have a companion star because there's enough stuff in that nebula to create two stars. And if Jupiter had been big enough, our sun would have had a companion star. Jupiter, an important thing about Jupiter is it's got, 62, 64 moons? I don't know, lots of moons. But there are 4 very important moons around Jupiter. And they are moons that Galileo saw, and so they are called the Galilean moons. So listed from closest to farthest, we have Io, Europa, Ganymede, and Callisto. Okay. So the gaseous planets, you can't stand on them. Their surface is basically kind of where their surface is you cannot stand on. Their surface is gas. Jupiter has these kind of cool banding features. So I'll kind of direct your attention to Jupiter's bands. Of course, you kind of see the stripes. And through a telescope, a decent telescope, that's one of the things that you like seeing about Jupiter. As it turns out, these actually, they're called belts and zones, and they go opposite directions. Okay, they kind of alternate. Is that not weird or what? Okay, but they do. And you kind of see the composition of the clouds. An important thing about Jupiter is their great red spot. And you can see the great red spot right up here. And it's been going on for over 300 years. I'm like, really? Really? So through a telescope, like I said, you see the banding features of Jupiter through a telescope. Oftentimes you'll see this spot. Again, I have a lot of geeky friends at the observatory, and you can actually look at what time the spot is going to, what we say, transit, go in front. So you know when the spot's going to go across. And the other thing is you'll see Jupiter, and then you'll see these these things, and oftentimes these things kind of lie, these little red dots that I have here, actually these would be the Galilean moons. So that's kind of cool too. On to Saturn. Of course, Saturn has the coolest rings, but all of the gas giants have rings. Saturn has some awesome moons, and I have a picture to show you. Two of the Saturn's rings, moons. Two of Saturn's moons, Titan and Enceladus. Titan looks like this. So remember I said that, I said we have an assortment of, NASA has an assortment of spacecraft. So does ESA, so does China and India. But, so anyway, the moon, Titan, actually has been visited by a spacecraft called Huygens. And this is what the surface of Titan looks like right here. So Titan, the moon. When it comes to like landing on something and our gas giants, those planets, you can't land on them. So land on the moons. Okay, so Titan actually has a cycle not of water, but of liquid methane. It's really weird. Okay, and then this is Titan right here. And that kind of blue right here, if I'm thinking about this right, that actually is a lake of liquid methane on Titan. Road trip. So another moon orbiting Saturn is Enceladus. So these two photos are Enceladus. It's got these cool looking tiger stripes right here. So it's thought, do they look kind of blue underneath there? Okay, so it's thought that actually under kind of the icy rocky crust of Enceladus actually is liquid water. Is that not cool or what? There have been movies about Enceladus, like science fiction movies. So here's Enceladus. Here's actually Enceladus looking at it, and this, I don't know how long ago these were, maybe, I don't know, 2010, something like that, not that long ago. Basically, the little geysers of liquid flying out from underneath the crust and freezing as they go out. That is just amazing. So Enceladus. So the rings, Saturn's rings, which look very pretty through a telescope. Again, anytime we see a planet, even the gas giants, they are not creating their own energy. Basically, the sun is hitting them, and we're seeing that light come off. So the shinier it is, or the more reflective it is, the more light we're going to see. So we see the rings because actually they are icy particles. The thing about the rings, though, is sometimes you see the rings. Sometimes you see the rings like this, okay, but sometimes they're called, that would be more like face on, but if they're edge on, they're like this, and you can't see the rings, you basically see a line through Saturn. So if they're like this, that's cooler. And the different orientations are because Saturn is orbiting the sun too, so we're kind of privy to different orientations. All right, the blue dudes. So after Saturn, we have Uranus, and here is a photo of Uranus. Ariel is a moon that orbits Uranus. Both Uranus and Neptune are blue because of the presence of methane, which is like the liquid that's on Titan, right? So Uranus, I think I mentioned the other day, if you're to look at Uranus, and you can probably see kind of the, Uranus actually, if this is the sun, and this is the plane of the ecliptic, and because the Earth orbits the sun like that, and most of the planets lie pretty much on the plane of the ecliptic. The axis of rotation of Uranus, I said, is basically laying down. Okay, so it's rotating on its axis, and it's going like this, which is pretty crazy. Sometimes students will say, really? So here's the deal. Can you see where right now this hemisphere has summer, okay? We're going to go counterclockwise, okay? Now that same hemisphere has winter, okay? But that is just, now it's equinox, Okay, so that is craziness. But most likely it did that because it was knocked over early on. Definitely all the gas giants have rings. We saw Saturn's, here's Uranus's. Jupiter has rings too. Now, what is there to see? There's something definitely see of Jupiter through a telescope. There's something definitely see of Saturn through a telescope. These guys, Uranus and Neptune, the best thing you can do is basically you saw the planet. It's like a disk. And you can kind of see it does look different than a star because it's like I said, kind of a disk component. All right, Neptune. Neptune's blue, and it's also blue because of the presence of methane. Neptune is the outermost official planet, but sometimes actually Pluto comes closer to the sun than Neptune just because of its strange sort of orbit. So this is a photograph of the surface of Neptune. A lot of these photographs, like this one, actually were taken by flybys. The Voyager 1 and Voyager 2 missions, like I said, they're leaving the solar system. Basically, they take these pictures and send them back, and then they go on about their way. You can see kind of a great dark spot there. Instead of lasting 300 years, though, those are more transient. They don't last all that long, and then they go away. Neptune has the fastest wind speeds. Neptune's moon of note, actually, I'm going to show you, is Titan. Oh, no, darn it. Nope. Sorry, change that. This should be Triton. Final answer, Triton. Okay? So Triton, because Titan is orbiting Saturn. My bad. But it's called a kind of a cantaloupe feature. So this is kind of like the cantaloupe feature they're talking about. Okay. So again, what's it going to look like through the telescope? Not much. A blue disk. Okay. So I have a slide on Pluto, but I'm going to hold that back. This is actually the other part of your assignment. So on page 480, if you would, answer